Now we're going to talk about force vectors. Got a rubber band here between a couple of hooks. Actually, the hooks are just a couple of paper clips. I keep those around. I use a lot of rubber bands and paper clips. Okay, so I stretch this thing out. Now there's a force being exerted. Now let's take the force being exerted on my right hand. That force is in this direction, the direction of a displacement vector from this end of the rubber band to that end. So that if I put a point here and use this for the initial point and stretch the rubber band out, I've got a terminal point up here somewhere. Okay, so when the rubber band is stretched out from this initial point to this terminal point, there's a certain force. And that force is in the direction of the displacement vector from this point to this point. So I can sketch that displacement vector. Okay, now this point has coordinates and this point has coordinates. And this displacement vector then has certain magnitude and angle. And the magnitude of the displacement vector is the length of the rubber band. So let's write some of that down. Okay, so the rubber band goes from this point, is stretched between this point and this point. Let's let this point be x1, y1, this point x2, y2. We can slap down a coordinate system, and it doesn't matter where the origin is. We can get the coordinates of this point, the coordinates of this point. The coordinates of our displacement vector, or the components of our displacement vector, aren't going to depend on where we put the origin of our coordinate system. It's just going to depend on how far we have to go in this direction, how far we have to go in this direction to accomplish this displacement. So, as we observed, the force at this point, the force on my right hand, is in the direction toward this point. So we say that the force exerted at the point x1, y1 is in the direction of the displacement vector x2 minus x1, y2 minus y1. x2 minus x1 being the displacement from here to here, y2 minus y1 from here to here. Now, that force vector I'm going to indicate by an orange vector in this case, and it's going to be in the direction of this vector. It's going to have a completely different scale. It's not going to be a length. The displacement vector, the magnitude is the length. But let's just draw that force vector. We can draw it at any length we want. Let's draw our force vector right here. Okay, so that's the force exerted in point 1 in the direction of point 2. So I'll call that F12. Now, by knowing how much weight the rubber band is supporting, and by measuring its length with different weights, we can see how its length changes with the force exerted by gravity on the weights here. So put a weight on, rubber band gets longer. I put on another weight, the rubber band gets somewhat longer. So I can determine the pattern of length versus supported weight. I can actually draw a graph of that. I can model it with a function. I can do all kinds of things and determine from this length of this displacement vector how much force was being exerted by the rubber band, how much tension there was in the rubber band, that tension then pulling this end this way, pulling this end this way, and we're interested in the tension exerted on this point, which is going to be in this direction. So we could observe the length of the rubber band versus the amount of supported weight and use the trend of our data to determine with some degree of accuracy the force based on the length of the displacement vector. I use the word from. I kind of like based on better than from. I didn't know I was going to prefer this wording until I read it. That didn't like the word from. Okay, but we understand that the trend of the data will allow us to determine how much force is being exerted when the vector has the length of this displacement vector. Okay, now I've measured my displacement vector, and I think it has components pretty close to 9 centimeters and 10 centimeters. So what's its magnitude? Okay, well, you could calculate that. And hopefully you calculated that as I paused. The magnitude, or the length in this case, is the square root of 9 centimeters squared plus 10 centimeters squared. And that's equal to the square root of 181 centimeters squared. But when I take the square root of centimeters squared, I get centimeters. And the square root of 181 centimeters is roughly, give or take a tenth, 13.5 centimeters. Now, if I load this rubber band until it stretches to a length of 13.5 centimeters, or if I've got data on that rubber band, and assume that that rubber band isn't going to change from one moment to another, but although it probably does, then I can determine the associated force. So from measurement, we get an associated force, which I estimate to be about 12 newtons. So what is the component of a 12 Newton force in the direction of the vector 9 centimeters, 10 centimeters, direction of this displacement vector? You should calculate that. Okay, you might or might not have thought of this, but since the force vector is parallel to the displacement vector, it's going to make the same angle with the positive x-axis. So we can easily determine that angle as the arctangent of 10 centimeters over 9 centimeters, and in degrees that comes out very close to 48 degrees. Now we know that the force vector has magnitude of 12 newtons and direction 48 degrees. So what are the components of that vector? If you haven't gotten it, F12x component is magnitude of F12 times the cosine of theta. And similar expression for the y component. So once more, what do you get? Well, F12 times the magnitude of F12 cosine of theta. Magnitude of F12 is 12 newtons. Theta is 48 degrees. We get 12 newtons times the cosine of 48 degrees. And the y component is the magnitude times the sine of the angle, which is going to be 12 newtons times the sine of 48 degrees. And I believe this comes out about 8.9. And this one, I think about 8.1. And that's newtons in both cases, because of course we're multiplying newtons by a pure number, and we're going to get newtons as the unit of our result. Well, okay, well, we get 8.0 newtons and 8.9 instead of 8.1 and 8.9. I was doing a mental approximation and just was off a little bit there. Okay, and the approximation I did, incidentally, was just based on the ratios of sides of a triangle and the sides of this triangle. The magnitude of this triangle is 13.5, so the cosine of the angle will be the 9 centimeter x component divided by the 13.5 centimeters. The y component will be 10 centimeters divided by 13.5 centimeters, and then multiply those ratios by 12 newtons. And we can do the approximation if we've got a little bit of mental arithmetic, but the approximation could be off. Okay, so to two significant figures, those are the components of the forces. Now the question is, why would we want to find the components the components of that one force, that 12 Newton force? Why would we ever want to find the components of a force? Well, what if I decide to stretch out a second rubber band? Now, there's going to be a thinner rubber band. I'm going to stretch it all the way out to here. So now I've got this thinner rubber band. I'm going to stretch it out here. And I could get these coordinates, determine the length of this rubber band, and then hang weights from this rubber band one way or another, figure out how much force it's exerting at that length. Having done that, I want to know what the net result of this force and this force is. Well, the net result of these two forces is just going to be the sum of the two force vectors. So if I know the components of this force and then go through the same process with this force to find its components, I can find the net force, the net result of these two forces. And I can use that to do a lot of other things. So I've stretched the thinner rubber band out to the point x3, y3, and I don't know, I haven't measured it, don't know just how much force that thing exerted in comparison to this force, but I don't think it was as great. So I've got a force here that I'll call F13. And this force is going to combine with this force to give us some net force. And we're going to go ahead and calculate that in the next video. So the main purpose of this video is to show how we can use magnitudes and angles and get information related to the forces that a rubber band can exert. And of course forces can be exerted by other things other than rubber bands, and it's a general and very important part of physics to determine how forces combine. Another thing you can anticipate in the next video is I'm going to talk about the use of unit vectors. It turns out we don't really need to calculate the angle theta. We can just calculate a unit vector in the direction of this vector and multiply that unit vector by 12 newtons, and boom, we have our two components. And we could do the same thing, of course, with the vectors over here from our new rubber band. More about that shortly.